in the way to sustain.
Wave-particle duality showed us that energy refuses to behave as only a wave or only a particle. Then quantization forced us to accept that energy arrives only in specific allowed steps, the packets we call as quanta. Now, to understand reality further, we must confront a third idea, the uncertainty. Classical physics began with a simple belief. If something exists, it must have a definite position and a definite motion at the same time. Any uncertainty, classical physics assumed, comes from poor measurement and not from nature itself. But wave particle duality already challenged this belief because position belongs to particles while momentum in quantum physics is tied to wavelength, a wave property. So, an unavoidable question appears. If something behaves like wave, how do you even define where it is? A single wave with one wavelength spreads endlessly through the space. It has a perfectly defined wavelength and therefore a perfectly defined momentum, but it has no location. There is no here in this pure wave. The key is to create something that appears localized. The wave itself must be structured differently. A localized quantum state is formed by combining many waves of slightly different wavelengths. Where these waves overlap strongly, a concentrated region appears. That region is what we call position. So, position is not fundamental. Position is the result of interference. But this immediately creates a consequence. Each wavelength corresponds to a different momentum. So when many wavelengths are combined to create position, many momenta are combined as well. This happens before any measurement is made. It does not depend on observation being on or off. The tighter the position becomes, the wider the spread of momentum becomes. The clearer the momentum becomes, the more spread out the position must be. This natural limit is written as delta x dot delta p is greater than or equal to h dash by 2. Here, delta x represents how localized the wave is, delta p represents how spread out the momentum is, and h dash, the Planck's constant, divided by 2 pi. This sets the scale at which wave behavior becomes unavoidable. This is not an experimental limitation, it is built into the structure of waves themselves. So, the key realization is uncertainty does not arise because we disturb a particle while measuring it. Uncertainty exists because precision in position and precision in momentum are not independent properties in a wave based universe. Their precisions are inversely proportional. Wave particle duality told us energy is not a single classical entity. Quantization told us energy is not continuous. Uncertainty now tells us something deeper. The energy cannot carry both precise position and precise momentum at the same time. So the question remains the same question we raised before. Is quantization the final description? Is uncertainty the deepest rule? Or are these only surface patterns of something still deeper? Is reality fundamentally discrete or continuous in a way we do not understand yet? Or are wave particle and uncertainty simply human labels, temporary tools we use to describe something far stranger? As of now, physics gives us its most honest answer. We do not know, and we are open to finding out. Uncertainty is not a weakness of physics, it is a doorway into the structure of reality. In the next videos of this playlist, we'll move forward into superposition, quantum probability, quantum entanglement, tunneling, and so on. Ideas where uncertainty does not disappear but becomes even more powerful. Let's face the uncertainty, let's keep questioning, let's innovate to sustain. Don't forget your formalities to our channel. Nandri, Vanakkam.